Okay, let's go ahead and get started recording with polynomial functions. So this is section 4.1, so I know we're kind of going backwards. So we've already done adding, subtracting, multiplying, and division, and now we're going to kind of learn about polynomial functions and graphing. So if you remember that we had certain rules that we had to follow to determine if something was a polynomial function, and that is that the power has to be positive. We know that the power has to be an integer. So it can't be a fraction, integer. So it can't be a fraction, it can't be a square root or anything like that. It has to be an integer. So no square roots, no roots, nothing like that. So something that we would look at as a polynomial, we would have something like f of x equals 3x to the fourth minus 2x to the third plus 3. So that would be a polynomial because we have an integer. Those powers are both positive, and it doesn't matter about the coefficients. So the coefficients can be positive or negative. They can be square roots. They can be anything. So that's what we're looking at when we're looking at the rules for a polynomial. Again, another thing that they can't be, of course, it's integers. So this would be a big no. So a big no, I should probably just put a no there, that we can't have something like this, y equals negative 2x to the negative 4, because we can't have negative powers. We cannot have y equals 3x to the 1/2 power, which means square roots. We can't have those kinds of things. And of course, this really identifies that we also can't do something like this, negative 3 over x to the third. Because remember that if we have a power in the denominator, if I want to bring it up, I have to make it negative. So that's really negative 3 x to the negative 3 power. So we can't have those. Okay, so those are the rules. Terminology, power function just says that if we have a function of the form f of x equals a times x to the n power, the only thing that has to be true is a and n are not 0, and they have to be real numbers. So that means they can be anything except 0. So I can't have 0x to the 0, obviously, because 0 zeros everything out. X to the 0 just becomes 1. We don't have a value there, so we can't have that. So it has to be non-zero real numbers for it to be a power function, which means it has to have a power. And if you recall, x to the 0 is just 1, whereas x to the first is just x, and x squared, of course, is just x squared. So we have those different things, and of course, for it to be called a power function, it has to have a power. X to the 0 is not considered a power. Okay, non-zero real numbers means that they can be negative. Okay, a monomial is this one. It just means that we really have this, but it has to be one term. So I have y equals 3x squared y. It doesn't matter, just as long as I don't have anything adding to that. That's considered one term. That's considered a monomial. A polynomial is a monomial, or it's one, or it's more than one monomial, so it can have multiple terms. So basically, it just means that we can have multiple terms. Standard form of a polynomial is order of greatest to least power. I don't like to use the word degree because really it's really the greatest to least power, because the degree is really the first one, which is the greatest one. So that kind of confuses you a little bit. So greatest to least power. If we have, of course, x squared y cubed, the power of this term is 5 because we add up those powers. Okay, but only if it's that. If I have x squared y plus xy, the power of this one is 3, the power of this one is 2, and that's it. They cannot be combined together. Okay, the degree of the polynomial is the greatest degree of any term. So notice in this case, if this was my function, my degree would be 3 because that's the highest one. Okay, my degree on this one is also 3, right? So it's the greatest degree of any term, not all the terms combined, just one particular term. And then a polynomial function is something that's continuous. So we haven't really talked about continuous. So continuous is a function that looks something like this, meaning there are no breaks in the function at all in the graph. Okay, so other terminology, beginning and end behaviors. So the book goes into end behaviors. And the way the book describes end behaviors is that we have a graph, and this is one end, and this is another end. And in between, we have a bunch of stuff going on. It doesn't really matter. But basically, this is the end, and this is the end. Well, I think that gets confusing. So I'm going to be calling this the end, and I'm going to be calling this the beginning. So that's the beginning behavior. At the other side is the end. So you can see at the beginning, the function starts one way, and then it continues all the way down to the end. So we're going to be doing it as the beginning and the end behaviors. Now, how do we write those? So notice here that x, of course, is going to the left. So as we progress from 0 to the left, meaning that as x goes to negative infinity, so x is going to the left as far as it possibly can go, and that's the farthest it can possibly go, you'll notice that y goes positive. And that's only for this particular example. It's not always true for any function, but notice as we go this way, y is going up, right? And y is going that way. Okay, as x goes to the right, we can see that y goes down. So rewriting it the same way, as x goes to positive infinity to the right, y goes to negative infinity. And again, it's only in the example that I've given you. So there's other functions where, for example, if you look at, well, this one here, as x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y goes to positive infinity as well. Y is going up. Okay, so that's what's happening with those functions. Okay, the zeros are where it crosses the x-axis. So we have a 0 here, a 0 here, a 0 there, 0 there, a 0 there, a 0 there, and a 0 there. So notice in this example, we have 1, 2, 3, 4, 5, 6, 7 zeros. So where it crosses the x-axis are considered my zeros. Those are also called my solutions. Okay? Those are also called my x-intercepts. So basically where it crosses the x-axis. Remember that the y-intercept, which is located right here, is where the function crosses the y-axis. And that's an important point as well. Remember that for a function, it can only cross the y-axis one time. So you can only have one y-intercept, but you can have multiple x-intercepts. The domain represents the x values. The range represents the y values. So if you notice in this particular example, the domain runs all the way from negative infinity because it's continuing in this direction, and it's going all the way up to positive infinity because it's continuing in that direction. So we have negative infinity is less than x, which is less than infinity. That's also considered all real numbers because anything works. And then for the range is where it goes up or down. So notice in this case, it goes down to negative infinity. So that's the lowest number it goes down to. And the highest number it goes up to is positive infinity because it goes positive infinity here. It's not really, notice I'm not really doing beginning to end. I'm just figuring out what's the lowest number. The lowest number is going to be located down here. And the highest number is going to be located all the way up here. So that would be considered the domain. This is also all real numbers. Just for this example. Again, this example is just one example. We'll do other examples as well. Okay, so that takes care of that. Those are all the definitions, and that's what we talk about here. So I just want to kind of go into that a little bit. So you'll notice that if the degree is even, so notice here we have y equals 1/4 x to the 4th. Notice that that's an even number. That's a power. That's the degree. Notice that the leading coefficient in this case is positive. The leading coefficient is the number in front of the x to the 4th. That's a positive there. So that tells me that the end behavior goes up. Okay, remember the end behavior is on the right. So it's that little value right there because I don't want to put too many arrows. And then because it's an even degree, because it's to the 4th power, that means that the beginning behavior also goes up. So notice that we first find the end behavior, which is the right side. So we find the right side behavior first. The right side behavior tells me it goes up because of that positive, because plus means up, minus means down. And then on the left-hand side, which is my beginning behavior, because this is an even number power, then it also goes up. So that means my function is going to look something like that. Okay? Not always exact, right? I didn't get exactly what they got. It's going to look something like that, though. Okay? If the degree is odd, so notice we have y equals x to the fifth. Okay, first off, notice here, this is a positive, so that tells me my end behavior goes up. Y to the fifth, because that's an odd power, that tells me the beginning goes the opposite direction of the end. And notice it goes down. So the function could look something like this. Now I'm going to draw it a little differently than what they did. I'll draw it like that. Okay? So it could look like that. The only thing that's important is that we know that the end behavior is up because of that positive, and the beginning behavior is down because that's an odd number. And so you'll notice that this particular function changes directions once because it goes up and then it goes down. So that's one change. And then it goes back up. That's two changes. Notice that it changed twice. Okay. So how do I know how many of those it can potentially do? Well, we take a look at the power, subtract 1. So 5 minus 1 equals 4. That means that there are 4 that the function could, doesn't mean it will, but it could change positions 4 times. Okay. Now it can notice in our function, it changed twice. So it could change 4 times, it could change 2 times, or it could not change at all. Okay. All those are possibilities. Notice that this function goes up and up and up and up. It hits 0 and then it keeps going up. So basically it always goes up. So this one always goes up. So this representation, which is x to the fifth, which is the actual representation, not mine, but it is the actual representation, tells you that this function is always going up. So it never changes directions, which remember was okay because it can be 4 and then we go down by 2. So then it can be 4, it can be 2, and then we go down by another 2, or it could be 0. Okay. Now notice what happens when the leading coefficient is negative. So when the leading coefficient is negative, notice that this function is going down. Okay, notice when the leading coefficient was positive, the function was going up. And why is that? Because when it's positive, the end is going up. And because it's an even function, the beginning and the ending do the same thing. So in this particular case, notice that we have an even function. Okay, but the leading coefficient is negative. So that tells me that the end is going down. Because it's even, we know that the beginning is also going down, so it's going to look something like that, okay, which is what it does. Same thing on this one, because it's odd, we can see that first off, it's odd and it's negative, so the negative tells me it's going down no matter what. Odd is telling me that on the beginning end, it goes in the opposite direction, and so therefore, it could look something like that. We don't really know what that middle means, but we know the end behaviors, and we know that information. Okay, so that gives you all the definitions of 4.1, and now we're going to do some problems.